Howdy. This is Mr. Potter. Today we're going to talk a little bit more about differential equations, but we're going to talk about one very precise application that's used quite a lot, and it's called Newton's law of cooling. What I want to do is I want to do a real quick recap of what we talked about in our previous lesson. The idea of how do we actually go about solving a differential equation. And the first thing that we're going to do is we're going to separate our variables. So let's say that I've got a differential equation like dy dx equals xy squared, and I know this passes through the point 1, 4. So the first thing I'm going to do is separate my variables. So I'll have dy equals xy squared dx, and then move the y squared over. So this is y to the negative 2 dy equals x dx. My first step is to make sure all of my dependent variables are on one side of the equation, and all of my independent variables are on the other side of the equation. The second thing that I want to do is I want to take the antiderivative of both sides. So I want to take the antiderivative of this. I'm going to use the power rule and get y to the negative 1 over negative 1. The antiderivative of this would be x squared over 2. And I want to add the constant on the independent variable side. So my c is going to go wherever x is, or wherever t is, or whatever my independent variable has to be. So I'm going to put the constant on my independent variable side. And now once I've got this, I've got a relation here, but I really want a functional solution. So step 4 is to solve for y. So I'm going to take the negative of both sides, end up with y to the negative 1 equals negative x squared over 2. And you could put a minus c, but any constant, positive or negative, is still a constant. So I'm just going to continue to put plus c until we actually determine the value. And then I'm going to take the reciprocal of both sides to get y by itself, to get rid of this negative 1 exponent. So taking the reciprocal, it's going to be 1 over this expression, negative x squared over 2 plus a constant. So now that I have y by itself, the last thing that I need to do is I need to solve for c. So when I do that, I'm going to be taking the initial values that I've got here. X is 1, and y is 4. So I end up with 1 over negative 1/2 plus c equals 4. And I'm going to solve for c. I'm going to take the reciprocal of both sides. So I end up with 1/4 equals negative 1/2 plus c. And then I'm going to move this 1/2 to the other side, leaving me with 3/4 equals c. And so once I've actually solved for c, now I can place it where I've solved for y and actually get an explicit function of y. Y as a function of x is equal to 1 over negative x squared over 2 plus a constant. And of course I could write this as 1 over 3/4 minus x squared over 2. Or I could even refine this a little bit more by taking this and kind of getting a common denominator and flipping it, so I'd end up with 4 over 3 minus 2x squared. So this is going to be a little bit more like what we expect to see, but any of these three solutions are perfectly acceptable once I've replaced c with 3/4. So this is the idea of how we go about solving a differential equation. So what I want to talk about now is I want to talk about Newton's law of cooling. Now the whole idea behind Newton's law of cooling is that whenever I'm trying to either cool something down or to chill it up, my rate of change of temperature with respect to time is not only dealing with the temperature, but how far away we are from some ambient temperature. So what I'm going to find is that my change in temperature with respect to time is equal to a constant times the difference between the current temperature and the ambient temperature. So for our purposes, TA is my ambient temperature. So in other words, this is going to be my temperature in my room, or the temperature in the oven, or the temperature in my refrigerator or freezer. And whenever I talk about T, that's going to be my current temperature. But we'll also be talking about T sub 0, which is my original temperature. In other words, the temperature of my item before I started heating it up, or before I started cooling it down. So I've got this differential equation, dt dt, the change in temperature with respect to time, is equal to k times how far I am from the ambient temperature. And this is actually going to prove to be an interesting graphical solution, which we'll talk about in just a few minutes. First things I'm going to do is separate my variables. So I'm going to have to move this t minus ta to the denominator over here. And I'm going to have k dt here. And I want to integrate both sides. Integrating this left side, I'm going to have to let u be t minus ta, but the derivative of that, because my ambient temperature, my room temperature, is constant, or we're going to assume it's constant. We're going to assume little fluctuations don't affect. This is just going to be dt, which I clearly have. So this becomes the natural log of u, the change in temperature between my original temperature and my ambient temperature. And over here, the antiderivative of a constant would just be the constant times t plus another constant. Keep in mind that this constant here is my scale constant. In other words, this reflects how I'm heating or how I'm cooling. And this constant over here deals with my initial values. This is the constant that we've been dealing with in the previous lessons. But this constant has to be given to you, and it's going to be positive or negative, depending if we're heating something up or cooling something down, respectively. And then I have to solve for t. So what I've really got here is I really have t minus ta is equal to the exponential of this other side, which is e to the kt times e to the c. And I don't really want to call it k. Let's just go ahead and call it a, e to the kt. Because what's really going to happen here is at t equals 0, my temperature is really my original temperature, and this becomes T0 minus TA is equal to A e to the k times 0. And in other words, just A. So A is really the difference between my original temperature and my ambient temperature. And so what we have here is Newton's law of cooling. Which states that the difference between the current temperature and the ambient temperature is equal to the difference of my original temperature minus my ambient temperature times e to the k times time power. And so this is my Newton's law of cooling, and I know even though it says cooling, we can use this to describe situations where we're heating something up as well as cooling something down. But in our example, what we're going to be talking about is soup. So, I've got some soup at 90 degrees Celsius, and it's going to cool to 60 degrees Celsius when the room temperature is 20 degrees Celsius. So, with this information, what I know is my original temperature is 90 degrees Celsius. My ambient temperature is 20 degrees Celsius. And the current temperature of my soup is 60 degrees Celsius when my time is 10 minutes. So I have enough information here to actually solve